Hello, welcome to this FirstEDA video. My name is Richard Boileau. Today's subject is functional safety and how formal verification can play a crucial role in identifying systematic faults and random failures as may develop once a chip is in use. Joining me today is Dave Kelf, VP of Marketing with OneSpin. Dave has an MSc in microelectronics and began his engineering career with Plessey and Nortel before moving into marketing with Synopsys and Cadence. Dave also established his own wireless IP company. OneSpin is a formal verification company with a range of verification solutions, and FirstEDA is OneSpin's value-added distributor in Northern Europe and specialises in verification and validation solutions for FPGAs and ASICs. Hi Dave, many thanks for joining us today, really appreciate it.
Thank you, Richard. It's good to be here.
Oh, it's a pleasure, it really is a pleasure. Verification is of course important within lots of sectors that have functional safety. It's given rise to a number of standards within the different industries. Mm-hmm. Could you take a moment please, Dave, to explain or recount what your customers are doing, what OneSpin's customers are doing in this space, please? Okay,
so well, we work with a number of companies doing all kinds of different safety critical area, designs in different areas. So for example, we have companies working in the automotive space, obviously, working with the ISO 26262 standard. We have a number of companies in the aeronautical space working with DO 254, and also slightly more unusual ones such as companies doing instrumentation for nuclear power stations who would adhere to a different set of IEC standards, medical devices, defense, and so on. So quite a range of companies doing safety critical work in different areas.
Excellent. No, thank you for that. And of the various sectors out there, ISO 26262 has just come along. That's a relative newcomer.
Yes, indeed.
And I understand that OneSpin is very close to the automotive sector. Could you remind us just of why that is, please?
Well, that's right. So OneSpin actually originated as a group inside Infineon. And it was the Infineon group working in the automotive space as well as other areas that decided they needed a formal verification capability. Because formal verification, of course, has special capabilities which are very effective for these kinds of designs which have a very high verification requirement. So OneSpin started life as part of Infineon, got spun out, and has become an independent company, but then of course still maintains its very close connections with that particular automotive group as well as automotive groups in a number of other companies.
I see. Okay, thank you. Before we look at functional safety in the whole automotive space, one thing I'm quite interested in really is why, for example, the automotive sector hasn't adopted the functional safety standards that have already been embraced by, say, the aerospace industry. Surely they can accept those in toto. I mean, or are there kind of different drivers?
Yeah, I think there are different drivers, Richard. So basically, if you look at the aeronautical space as a good example, the airplanes generally have systems which have a lot of redundancy built in. So you'd have a number of sort of equal systems, a major one actually performing whatever function is required, a second one which is the same function monitoring that, and then the third one which can step in if the second one detects an error or detects a difference between the two functions that are working. So they employ this a lot. They have the space to put these different computers all over the aircraft, and so that works quite well for them. On top of that, they don't have the competitive constraints that the automotive market does today. So in the aerospace industry, the pilots, once they're happy and they're working well with the controls in the aircraft, they don't change very often. It takes many years actually to make changes inside the avionics in a plane. On the other hand, in the car industry, especially nowadays, new cars are coming out all the time, and the various car makers are now differentiating the cars based more on the electronics than on the mechanics of the actual vehicle. So it means that the competitive space is very, very hot. On top of that, especially in the US, with the new kinds of lease deals that we see with cars, people and companies actually are changing their vehicles more frequently. So it's quite possible, especially in the high-end car market, for someone to get a new car every 2 years. In the US and in other countries as well. So therefore, the cars have to stay very current and make sure that that they've got the latest gadgetry and the latest differentiators so they can compete in this very, very competitive market.
I see, I see. And so presumably, in summary therefore, I mean, it's really kind of time and volume to market. Those are the main issues
That's right.
with the automotive sector.
That's right.
And I take it the complexity is obviously rising at a similar rate to meet that as well.
Well, that's a great point. So it's actually been pointed out that the amount of software in a modern aircraft, such as one of the Boeing or the Airbus aircraft, is nowhere near as voluminous or complex as
Right.
that in a regular car. So nowadays, a regular Honda can have many millions lines of code. And something like 100 or 150 microcontrollers, whereas an
Wow.
aircraft, of course, has nothing like that number.
Okay, great. Well, thank you. Just dropping on to the standard again, 2626.2, it distinguishes between system faults and random failures. Could you explain those two aspects, please, Dave?
Yeah, good point. So systematic faults or the systematic design process is the classic IC design process that we know and love from many different industries, and so systematic verification relates basically to the verification of the device, making sure it's working correctly, that it's been designed properly, and that the tool flow is working correctly as well.
Right. So that's very much kind of designed as intended, or operates as intended, I should say.
That's right. But of course, the issue with safety criticals, it's like verification and steroids. You can imagine the requirements planning, the verification planning, the coverage analysis. All these things are exercised at a much higher degree than regular verification to make absolutely sure that really solid functional coverage is achieved at a very, very high level to ensure these designs are absolutely working correctly and can be proven to do so. So that's the systematic flow. The random flow is more the new part that I think a lot of companies are focusing on right now. And what this is making sure that the device, when it's operating in the field, won't be affected by some transitory fault occurring, maybe for some electromagnetic radiation or an interference, something like that. And so to achieve this, what designers are doing is building safety components into the device, where the safety components actually watch the device in operation and look for random errors occurring while the device is operating and fix those errors. And so to verify this, of course, it's a much more complex operation. What you have to do essentially is inject faults into the design during the verification process and make sure those faults are either trapped by the safety circuitry or that they don't propagate to a place where they can actually do harm. And to do this, the verification of this is a fairly new field, a new area, and this is the part of the process where I think both formal and other techniques really lend a lot of value.
Right. So presumably the verification techniques, I mean, they must relate to the device itself. If it's a pure hardware device, it's going to be susceptible to some forms of error, whereas a field programmable gate array, for example, with its SRAM, the memory cells might be corrupted in a different way. So presumably we can have single event upsets and single event latch ups. So does the safety mechanism really relate to the kind of device that we're trying to protect?
I would say that no, that you see these safety mechanisms in all kinds of different devices. However, it has become, I think, more prevalent in the large semiconductor devices that we see right now.
Yeah. So you mentioned you mentioned microcontrollers earlier. Presumably, the safety mechanisms could be implemented in hardware or software.
That's correct. And in fact, what you see is different kinds of safety mechanisms implemented in either hardware or software. So at the hardware level, triple modular redundancy, TMR for short, is a common practice, similar to the aeronautical space, but obviously on a much smaller level. Specific components, key components, are added to the chip in triplicate, and the outputs of them monitored to make sure that if one of them goes wrong, the other two are still producing the right result. Other mechanisms are used, such as error correcting codes. Hamming codes are often used to encode and then decode data going in and out of memory. So if a bit in memory flips, the Hamming codes can just perform a direct error correction of that. If it's a single bit. For 2-bit, of course, Hamming codes are tough, but even in that case, an alarm signal can be sent to a protocol stack essentially running in software. And then on the software side, there's all kinds of watchdogs and other mechanisms that have been implemented. Plus, usually the software in one of these safety critical devices actually monitors the alarm signals coming in from the different areas in hardware and the interrupts based on that. There's a protocol for handling different kind of errors should they occur. Be it, can they just afford to ignore it? Is it something which is occurring a lot? In which case it needs to go into some kind of service record, or to up the other end of the scale, where the driver needs to be notified that they have a fault, maybe in a braking part. They need to stop the car immediately and have it towed away. So all these things can be possible, and it's really an interaction between the software and hardware that allows them to achieve that.
Okay. Well, thanks, Dave. My next question really is regarding what role formal verification plays in detecting the systematic faults which may have crept in during the design phase or as part of the tool flow, as well as the random faults that happen once the chip is actually in use in service.
Okay, and that's a great question. So what we have to do, I think, is look at both of these verification flows to sort of understand where formal would fit. In the systematic flow, of course, as I said, it's verification on steroids. So the whole planning process for this part of the flow is handled usually in a much more rigorous fashion than for a regular design. You start with a requirements spec. The requirements are made very individual, very self-contained. They translate to implementation spec and a safety implementation spec as well. So each part of the requirements can be understood how a safety mechanism will be implemented to handle those. This then translates to a verification plan, and the verification plan often consists of very, very specific isolated tests. Now, from there, you need to create either a test bench for simulation or assertions for verification. The test bench, for that you would have to create a number, usually of directed tests, but of course using UVM and random test techniques, it's possible to sort of build up a set of tests as well. But there's a bit of a disconnect between the requirements and UVM tests often.
I see.
On the formal side, creating assertions, it's, I believe, easier to map assertions back to these verification plan requirements. So for each individual test, that can translate to one or a collection of assertions, which can then be run directly onto the formal tool. And in fact, OneSpin actually has a mechanism called operational assertions, which is based on System Verilog, which makes that mapping even more easy and tighter as well. So so then once you've got a set of assertions which are clearly mapped to the set of tests, running those in the formal tool will provide an exhaustive analysis of the actual design, unlike simulation where you have to make sure the test bench is completely covering the specific test scenario. Formal will provide a completely exhaustive analysis and also coverage metrics, and those coverage metrics may then be fed back to the whole verification plan, and from that you have a nice closed-loop coverage system which allows you to achieve sort of very, very high levels of functional coverage, which of course you need to meet the safety standards. So that's systematic.
So on the systematic fault, obviously if we're doing simulation, we'd be after 100% coverage to say, look, we have exercised everything. What are the goals in terms of the random the random faults, and how do we find them?
Yes, indeed. So the random is a completely different process, of course. So to find random faults, what ISO 26262 demands is that the final design at the netlist level has faults injected into it, and then how those faults are handled is analyzed, and what you have to do as an engineer is achieve a certain level of diagnostic coverage. So
Right.
ISO 26262 has certain levels of safety integrity called ASIL A, B, C, and D. For ASIL D, you have to achieve 99% diagnostic coverage, which means 99% of the net list must have had a fault analysis performed, and those faults analyzed to make sure they won't do harm. They'll be picked up by a safety mechanism or will not propagate to anything dangerous. So to do
Right.
this, many companies have used fault simulation up to now. Fault simulation is an old technique where faults are injected into the design, and the fault simulation is run to figure out how those faults behave, and that works pretty well, but it takes a very long time to run, and it still relies on a test bench. With formal analysis, you can also do a complete, well, firstly, you can use formal to prune some of the more difficult to find faults from the fault list and then pass the rest to fault simulation. So that improves the process significantly, both in terms of being a more rigorous process and much faster as well, because you take out the hard to track faults from the fault simulator and do that with formal analysis up front. So you
Right. So
can do that.
you've reduced the workload.
That's right. But also, you can use formal to inject faults basically right across the design in the same way the formal tool would, the same way the fault simulator would work. And there, of course, the formal tool would just do an analysis for every single fault to make sure that the propagation paths from the fault to the safety mechanism to the outside of the chip are fully tested and are fully analyzed directly without the need for running simulation at all. So this is
Right.
really
Okay.
fault simulation. This is really formal verification used at the highest level for this kind of fault analysis.
So the nature of the faults, and this is thinking back to my aerospace days, single event upsets and single event latch-ups cause bits to get stuck at either 1 or 0, either temporarily or permanently. So are we saying we can inject faults and see how far they get clocked through the logic circuitry?
That's correct. So basically, the classic fault models are usually stuck at 0 and stuck at 1 faults. And these are the ones that actually will duplicate most of the kinds of faults that you might see. But of course, you can also inject transitory faults, single event faults, and so on, and do the analysis for that as well. And that may be important to make sure that a fault at a specific time, of course, while something else is going on inside the device, doesn't cause a particular problem that otherwise might not occur.
So to summarise that part,
Yeah.
Formal has a role in reducing the workload of simulation in terms of systematic faults, and where random faults are concerned, i.e. in relation to EMI or radiation, that what we're looking at is how the design can handle those faults, and
That's
be
right.
they temporary or permanent.
That's exactly right. That's right. And of course, you have to verify that it can handle that, and that's where formal can play a very significant role as well.
Dave, are there any concerns or issues regarding the tool flow, which must play an integral part in the number, or rather validating number, that gets churned out at the end of the process?
Yes, absolutely. So obviously the tools inside that flow must be proven to be completely reliable, so that a tool failure doesn't
Right.
actually produce some incorrect results, which will present a misleading result to the final certification process. So basically, the tool flow itself that's used for these safety critical devices has to be certified, and the design tools and then the verification tools on the side go through different certification processes. And this is operated by an organization called TUV, in general, who can go out and do a certification process and then basically provide a certification stamp, if you like, that the tool flow in use is satisfactory.
My next question for you concerns security. Functional safety and security kind of go hand in hand. We've already proven that the hardware fail-safe mechanisms work in their own right.
Yeah.
But ultimately, it's software that's having a major role in that. So if it's malicious software in from a hacker, then how can we verify that the hardware fail-safe mechanisms are still doing their job?
Yes, so that's a great point, Richard. Absolutely. So security is becoming obviously of greater concern for the automotive companies, and in fact, the ISO 26262 committee have been doing a lot of work in this more recently, and I think we will see requirements going into the standard in the security area as well. And the issue is obvious, of course, that a hacker can somehow break into the systems inside a car and either switch the brakes off or send it off the road or something like that. This has to be protected against. There's a number of security mechanisms out there. In general, what they try and do at the hardware level is check for the integrity of the device, that there's no unexpected paths or unexpected mechanisms whereby an essential function inside the chip can be attacked from the outside, or maybe from, as you say, some software call that was unexpected, passing through the registers and causing some problems. So the way this is often done, again with formal verification, is you can check all the paths from a specific area to the inputs, to the other parts of a device that can cause specific key registers and things like that, and actually check that no unusual malicious paths can occur, or that there's no path, say, through the scan chain or something like that a hacker can get access to. So a lot of these kind of mechanisms are now being built into the system as well, and are sort of being tested for, so the chip is being tested for security, a high security integrity level, and yeah.
I see. So presumably the system would be architected such that different parts of the system have different ASIL ratings.
Yeah.
I know from work I've done in the industrial sector that the highest SIL you can get tends to be hardware only implementations.
That's correct. Yes. Yes, that's right. So in automotive, everyone recognizes that there is a good deal of system software, of course, that has to be used. But I think a lot of the essential components. There's definitely a drive towards getting capability in hardware rather than software to ensure that both the highest safety and the highest security targets are met.
Right, excellent, thank you. And out of curiosity, I mean, where's it all going? You talk about how security may be kind of layered on, increasingly so moving forward. Where's this whole kind of space going in terms of functional safety in automotive? I mean, it's taken off at a huge rate.
Oh yes, clearly the industry has taken off, and it's also, as we said at the beginning, it's being driven by the competitive aspects of the car makers and them trying to introduce new ideas. And of course, the big one on the horizon, well, not really on the horizon, we see it today, is the idea of driverless cars. And we know that Tesla, Google, and other companies are doing a lot of work in this area right now. Driverless cars, of course, the kinds of functionality that's required there is even way beyond what we're seeing today in the highest end car.
Okay.
Basically, the safety critical capability built into the kinds of almost machine learning, artificial intelligence type systems that require for driverless car are extreme and significant. So we're going to see a lot more of those kinds of features, even if it's not a fully driverless car. A car that, obviously we have self-parking cars and things like that, but a car that can drive itself on the highway, that can navigate for sort of more well-known roads and wider roads, things like that, will all require these kinds of features. So I think that's one thing. I think we'll definitely see capability in terms of reducing the power of these devices. As more devices get introduced into a car, it's actually quite surprising that they're starting to use a large part of the overall power generated by the engine. Power is becoming a bigger concern, and also making the devices more robust so that they're not susceptible to electromagnetic interference and radiation and things like that is key as well, I believe.
I see. And presumably, talking about the number of devices that are present in a modern day car, from a designer's point of view, I suppose it's like it is elsewhere in the electronics industry, that there's a great deal of reusing IP, be it hardware or software. So design teams, again, having to reuse IP to hit those time and volume to market pressures that we spoke about earlier. So again, it's part of this big picture that we're having to kind of verify work done by other people.
Yes. So verifying other people's IP, of course, is a key issue for the IP industry in general, as we all know. And so for any IP that's being used in these safety critical devices, of course, all the safety verification, systematic and random type work that we've just been describing has to apply to the IP, and the IP must be delivered to the system house with the ACE or D certification intact. And that's basically what we're seeing today. So IP vendors working in the automotive space go through these mechanisms just like someone working on the final system on chip, and provide an ACE or D rating that's proven to the system house, who then has to prove that the full chip, including that IP, also meets the safety requirement.
Right. Okay. Thank you. Okay. And also, I get the impression that with the cars becoming more intelligent, driverless cars, that there's almost a bit of a tie-in to the Internet of Things. That
Yes.
the car then becomes part of a much bigger network, a bigger system almost. So, can formal verification play a role in just checking the internal workings of a chip, or can we be looking at the bigger picture and the communication protocols going on?
Yeah, that's a great question. So you're absolutely right. Of course, you can think of the car as being smothered in sensors, and although those sensors, of course, are being used within the car to do different things, there's no reason why a good number of them can't then be connected to the internet and provide data for different purposes, either back to the car manufacturer. And also maybe the service center where it's serviced, and also providing information to the drivers so they can understand their driving and that kind of thing. So I think IoT definitely plays a significant role. Formal is being used in a whole range of different applications right now. Although it's probably most well known for assertion-based verification and for equivalency checking, the automated apps that many formal companies are providing, including OneSpin, of course, are very effective for testing larger systems and ensuring that specific verification requirements in those systems are met. So there are capabilities for checking protocols, as we mentioned before. VIP verification, intellectual property that works with formal as a series of assertions for ensuring that the protocols are completely implemented correctly. These are all essential, and a whole number of other range of capabilities. I think in these apps are available today.
Okay. Well, many thanks, Dave. It's really been appreciated, your time here.
Thank you, Richard.
And I think we've touched on some great stuff there. I think my personal takeaways from this really are the role that functional verification has to play in the systematic and as well the random side. I mean that to me is this bigger kind of in-service issues and to a degree trying to guess what may be happening, or even just not knowing, and then having to come up with a way of handling anything that goes on.
Well, that's right. I mean, a parting thought on this is, high reliability, I believe, is important for any electronic system, and so of course, the work we're seeing going on in the automotive space, as well as some of the other safety critical spaces, I think will have a bearing on the entire electronics industry in the next 10, 15, 20 years as some of these features make it into other devices. Absolutely. So all the work we're doing here, if you're an engineer working on a communications device, a cell phone, anything like that, pay attention, because a lot of these capabilities are going to be coming to an engineering group near you, as it were, over the next sort of 10 years or so, I think. Yes.
That's fantastic. Okay, Dave. Well, again, many thanks for your time. It's most appreciated, and it's great to be talking with you.
Great. Thank you, Richard.
Very much.
Thank you, Richard. Nice to talk to you.
Thank you. Thank you for watching. We hope you enjoyed today's video on functional safety and formal verification. For more information on formal verification, please visit OneSpin's website. We also welcome feedback on today's video, as well as suggestions for other topics we might explore in the future. Thank you again.